Okay, Einstein summation convention part 2. This is actually going to be really fun. What we're going to aim to do today is figure out how to write the determinant of this 3 by 3 matrix in Einstein summation convention. So this determinant, this matrix, and as well as the expansion, the cofactor expansion, is in your notes. Just so you know, so hopefully you remember how to do the cofactor expansion. A 3 by 3 is relatively simple. However, I will never ever ask you to compute this by hand. That's what MATLAB is for. I strongly encourage you to learn how to do it in MATLAB. Otherwise, I guess you will have to do it by hand. But I will never force you to do it. So what we want to do is figure out how to write this in Einstein summation convention. So one thing that you're going to notice, you may have already noticed, is how on earth are we supposed to keep track of the negative signs? Because the first term is positive, the second term is negative, the third term is positive. And that's because we need another symbol. So the Kronecker delta is one that we introduced in lesson 2. So now I'm going to talk to you about the permutation tensor. And this is represented by the Greek letter epsilon. And it has 3 indices, I, J, K, or really any 3 indices you like, but I, J, K is the most standard. This is also called the Levi-Civita symbol. Just in case a book has it in a different way, at least you'll be able to look it up. So epsilon takes on 3 different values depending on I, J, K. So epsilon is 0 if any 2 of these labels are the same, or any 2 of these indices are the same. So say if you had epsilon 113, epsilon would be 0 because 2 of the indices are equal to 1. Okay, epsilon is equal to 1 if I, J, K, is an even permutation of 1, 2, 3. Okay, so what do I mean by that? I will explain that in 1 second. So epsilon is equal to -1. Hopefully you are tracking this pattern here. If I, J, is an odd permutation. Okay, so what do I mean by even and odd? So epsilon, let's say 1, 2, 3 is equal to 1 because it's an even permutation, okay? So is epsilon 3, 1, 2. So all I've really done is sort of shift everything to the right, and the 3 just sort of wraps around. So 3, 1, 2 is an even permutation. So you read right to left. Or sorry, you read left to right. So this is equal to 1 also is even. All right, so epsilon then 3, 2, 1 is odd. And hopefully that makes sense. So if you actually read the numbers in numerical order, 1, 2, 3, now you're reading right to left, and that's backwards, and so it's odd. Okay, so hopefully this makes sense. You'll have a little bit more practice on this one. So given this new notation, I'm going to just state outright how we would write this determinant using summation notation. So we're actually going to need 3 summation symbols. So you're starting to see why Einstein summation notation is helpful, because who wants to write 3 summation symbols every single time? So sigma I equals 1 to 3, sigma j equals 1 to 3, sigma k equals 1 to 3. And of course, spoiler alert, we're going to use this epsilon, I, J, K. And it looks like we're going to need some A's, right? So what it appears here is that I have an A 1, and let's just go ahead and call this first index I. So the first row, the first value is always 1, and then I let I vary from 1 to 3. All right, now I have A2. Well, I need I to be independent. It can't be tied to anything else. So we need a new index, and so I'll choose J. And then A3, which is the third row, it's always, the first value is always 3, and I'll let the second subscript be K. And this is actually how you would write the determinant of a matrix. So it's one thing to write it, it's quite another thing to prove it or believe it. So let's go ahead and test our equation. So I'd like you to, what we're going to do, and again, this sort of goes back to this idea that Einstein's summation convention actually really does help write loops. So I'm going to bring this term to the next page just so we have enough room to write. All right. So what I'm going to do is I'm going to fix I at 1. So let's write this in a different color. So I is fixed at 1. And what that means is I actually can, replace every instance of I with 1 and drop the outermost summation symbol because that is the one that allows I to vary. So I'm going to replace I with 1 and then drop the outermost summation symbol. All right, so let's see what happens. So what happens is we get sigma j equals 1 to 3, sigma k equals 1 to 3, epsilon 1 jk, a11, a2j, a3k. All right. Well, now let's fix J and see what happens. So we're going to fix J and do the exact same thing as before. Replace J with 1, and so I'm going to fix J is equal to 1, and then we're going to drop the outermost symbol now, the summation symbol, which is the J summation. Okay? So now what I've got going on now is I'm just left with K equals 1, 2, 3, the summation, epsilon 1, 1, K, A11, A21, A3K. All right. Well, now we can actually sum over K. And let's go ahead and write this out. So let's sum over K. And what we have is epsilon 111, A11, A21, and now all we're really doing is summing over K. So the terms that I just wrote down are always the same, right? Because I and J are constant, or at least the A11 and A21. And what I have for the first term is A31, because K is equal to 1, plus epsilon 112, A11, A21, A32. Now K takes on 2. Plus epsilon 113, A11, A21, A33. Okay, so let's go back to our rules here and figure out what epsilon is equal to. So if epsilon is, if any of the two indices are the same, that means epsilon is 0. So look what happens here. We actually sort of, we basically made our lives really easy or really unpleasant, depending on how you look at it. Because when we fixed J equals 1, we actually, we forced epsilon to be 0. Because look, epsilon 111 is 0, epsilon 112 is 0, and epsilon 113 is 0. And this is actually a really good thing not you notice when you go back to, I would encourage you to compare. If you look at the determinant, not one of these terms is in the determinant. And it's because epsilon actually forced all of those terms to 0 because they're not in the determinant. Okay? So let's try this again. And I'm just going to duplicate I'm just going to copy all of this over. So let's do this again, but let's do it to where we're fairly certain that we won't get the same issue with epsilon. And what we can do is we can really easily change this. And I'm going to erase. I would encourage you to pause this. But what I'm going to do is I'm going to erase from fixing j to 1. And now I'm going to fix j at 2. And let's find out what happens. So if I fix j at 2, what that means is I have k equals 1 to 3. That is the worst sigma ever. K equals 1 to 3 of epsilon 1, 2k, a1, 1, a2, 1, a3k. All right. So now we can sum over k again. And what we end up with is epsilon 1, 2, 1, a1, 1, a2, 2, a3, 1, plus epsilon 1, 2, 2, a2, 2, a3, 2, plus epsilon 1, 2, 3, a1, 1, a2, 2, a3, 3. All right. So now if we figure out, so you should kind of have this kind of in your head right now, but epsilon 1, 2, 1 is 0 because two of the indices are the same. Epsilon 1, 2, 2 is 0. But epsilon 1, 2, 3 is actually equal to 1 because it's an even permutation. So this is equal to 1. And the term a11, a22, a33, according to this, is a positive value. And if we go back to our, if we go back to the determinant, all of the cofactors, a11, a22, a33 is actually right here. So it works. Now, your exercise is going to involve a very special determinant, and you can exploit some of the ideas that you learned in this lesson. But hopefully this makes sense. And I look forward to hearing your response to exercise 4.